All right, let's take a look at a couple of problems from 6.2. So let's start with this one here. So we have a square matrix with orthonormal columns. And we want to show whether or not this is always going to be invertible, right? So if you remember a theorem from earlier on in the chapter, it's saying that a way to characterize orthogonal matrices, which are square matrices whose inverses are their transpose, right? This comes from that earlier theorem where if you have an matrix with orthonormal columns, that tells you that U transpose U or U transpose is the identity, right? So if we have a square matrix with orthonormal columns, this is actually going to be an orthogonal matrix, right? That's the question that we're trying to answer here. Because if it's invertible, then this will be true, and it will, by this theorem where this is the same as having orthonormal columns, we'll actually have this matrix being orthogonal. Let's think about this intuitively. So if we have a linear transformation whose columns are orthonormal vectors, the column vectors will look something like, maybe something like this here. And we're sending our basis vectors to that, right? So this is rotation, and rotations, if you're rotating some amount of degrees counterclockwise, rotating that same amount clockwise is the inverse. And similarly, another type of, if we pick different vectors here, we could have something that looks like a reflection. If we, instead of these two orthogonal vectors, we picked orthogonal vectors that look like, say, that, right? So intuitively, we think that all of these should have some type of inverse. But given just that the columns are orthonormal and it's a square matrix, how are we going to actually convert this intuition into a proof? Well, what's a fact about orthonormal vectors? If we have, if we have u dot v is equal to 0, oh my God. This tablet is acting up. Yeah, so if we have, say, u dot v equal to 0, does that tell us anything about the linearly independent or dependentness of u and v? If they're orthogonal, right, that means they're not going to be in the same direction. If they're in the same direction, there's no way that this could be 0, right? So these have to be linearly independent. But we have n columns, right, that are all orthogonal to each other. And that also means that these n columns, these column vectors also have to be linearly independent. And if you recall from the invertible matrix theorem, having n linearly independent column vectors is another criteria for being invertible. So in this case, this matrix we started with is going to be always invertible. And furthermore, it's exactly going to be an orthogonal matrix, right? We said an orthogonal matrix is a square matrix with the property that U transpose is U inverse, right? But from the theorem earlier in the chapter, that condition that U transpose is the identity, which is the same as you having orthogonal orthonormal column vectors, right? So these all these matrices U that have orthonormal column vectors also have this property that their inverse is equal to their transpose, and they're thus orthogonal matrices. All right, so next let's suppose that we have an orthogonal matrix. Say n by n. I want to say something about the row space now. So we want to show that the rows of U form an orthogonal basis for Rn. And this one is going to be 28 from 6.2. So if we know that U is orthogonal, we have a theorem that tells us that the inverse of U is now going to be equal to its transpose, right? So to say something about the rows of U, instead, we can actually make a statement about the columns of U transpose, right? Because the row vectors of U are the same as the column vectors of U transpose. So if we know that U is invertible, then its inverse is also invertible, because the inverse of the inverse is just U itself. So we have that U inverse is invertible, and in particular, that means that its column vectors are going to span Rn. So that tells us that the rows of U form a basis, right, for Rn. But we need to check that this basis is actually orthonormal. So how do we check that these column vectors we have are actually orthonormal? There's the theorem where that condition, column vectors are orthonormal, whenever we have, was it U transpose U is equal to the identity? Yeah. Right. But we know this is going to be the case because this condition here is implied by the fact that by this top condition here, where U inverse is equal to U transpose. So U transpose inverse, or U transpose transpose U inverse inverse, is just going to be U itself, right? So this statement here, this tells us that the column vectors of U itself are orthonormal, but because you can just take the transpose or the inverse of both sides, and this right side will be U itself, that tells you that the same is true for U transpose. So U transpose also has orthonormal column vectors. Which means that, in fact, the column vectors are an orthonormal basis for Rn. So the last problem I'm going to do for this section is 29. This is now about the composition or multiplication of orthogonal matrices. So let U be n by n orthogonal matrices. explain why u times v is orthogonal. So intuitively, we can, again, look at our rotations, our reflections, and kind of get like a sense for why this might be true. If we're rotating twice, right, we can view that as, say, oops, as two rotations of like however many degrees, or instead we can just view it as one rotation that's going through both of those at once, right? And if one's in the other direction, then you can subtract the angles instead. But for rotations, that makes sense. And similarly for if either of these contains a reflection, well, then the two reflections can cancel out. Or if just one of them contains a reflection, then you can compose the rotations, and then you have one matrix that's rotation and a reflection. So first, it's going to be pretty clear to see that UV is invertible, just because it's the composition of invertible matrices, or the product of invertible matrices, rather. Now, for it to actually orthogonal, this inverse, we know when this inverse exists, right? But this inverse now actually has to be the transpose of this matrix. So basically, we're just going to plug this in and actually check that this works out to be its inverse. So we need to check that UV transpose times UV is the identity. So just a little bit of algebra to expand this out. Remember, when we take the transpose, we have to switch the order. Or this is what we're trying to establish. So the left-hand side is, we know it's equal to this. And because U is orthogonal, we're going to be able to cancel these out because U transpose U inverse and get V transpose V, which similarly also cancels out to give you the identity. So these two do actually multiply to be the identity. And for square matrices, if it's a left inverse, it'll also be a right inverse, so we don't have to check the other side. So then we have that UV is also orthogonal. The last thing I want to mention is this is another homework problem. I don't think it was assigned. I won't go through the proof because it's a little bit computational and follows certain properties. But if you look at this mapping that sends, say, let's say we fix some W is the span of some vector, let's call it U. And then we take a vector Y and map that to the projection of Y in this subspace. This is going to be a linear transformation. I want to bring this up because a lot of times earlier when we are talking about like kernels and image space images and column spaces, a lot of times I mention linear transformations like, oh, you take like x, y, and map it to like x0, for example, where you would take some vector, oops, and send it to just its x coordinate, right? So we definitely have like seen this matrix a couple of times before, and really this all this projection business is kind of a more general case of that, where really we're taking some specific subspace W, and this represents some linear transformation where we're sending it to the smaller dimensional subspace. Just as before we took vectors in R2 and set them to this one-dimensional line, we're going to be able to do that for arbitrary subspaces in arbitrary vector spaces Rn. Moving on to 6.3, we're going to now start talking about projections onto these larger subspaces where W might be spanned by more than one vector. And formulaically, it's going to be very similar to how we projected onto one-dimensional subspaces. Before, if we had the projection of Y onto W, where W is span of one vector, we're just going to take this dot product and multiply U by this scalar value here. Similarly, if we have multiple vectors, we're just going to do this individually for each UI and sum them all up. And essentially what's happening here is if we have some subspace like this, say, plane here, spanned by two vectors that are orthogonal, then any vector, if we want to find the projection onto this, it's going to be good enough to find the projection onto these two lines. Because once we find those two projections, summing them actually gets us the projection we want. Because these all these vectors lying inside these lines here can we're able to span any vector in this plane using just scalar multiples of our vectors u1 un, right? What lets us do this is the fact that these vectors are all orthogonal, right? So we can just kind of add these together, and it's not going to essentially affect the overall sum. If they weren't orthogonal, then these terms would kind of interfere with each other, and you wouldn't be able to actually get this vector just by looking at these projections. Now, what if we impose a more strict condition? Not just that these vectors are orthogonal, but that these u1 through un are actually orthonormal. We actually get a really nice formula. So all of these are now going to cancel out because the magnitude of each of these vectors is 1. And now the projection is going to look like, whoops, the projection will look like, now we can just take y dot each individual vector and multiply it with that vector. And really, we can encode this even more concisely. If we write these U's as column vectors as U dot 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 U n. Well, these are all going to be these are linear combinations of U1 through UN. So we can write this projection as some weights times u, right? What are these weights? Well, these weights, y dot ui, this is actually going to be u transpose on y, right? Because the dot product is just, if you take two vectors, you can take the transpose of one and multiply with the other. And that's really what this, these scalars here, we can encode that in this matrix, or this vector u transpose y. So now we have this formula to compute this projection. We can actually say a lot more about this, this theorem, more than just how to actually find these coefficients. So this is a statement about actually all of Rn and not just one specific vector. But let's say we take any vector in Rn. So this vector, any vector and some subspace W of Rn. What we're going to be able to do is write this vector as a sum of two other vectors. This one vector that lies inside W, and this other vector that's inside the orthogonal complement of W. And this vector y hat is just given by that formula up above. Y hat is going to be the projection onto the subspace because that lies inside the subspace. And really this is, what this is saying is you're kind of breaking R into two parts. And these two parts, W and W perp, they're going to let you find any vector uniquely. So this vector, there's exactly one vector in W that corresponds to it, which is a projection, plus exactly one orthogonal vector that's given by taking the original vector and subtracting projection. And there's no other way to write this as a combination of vectors in W and W perp. So let's try and do a few true or false questions about W and W perp and this projection theorem. So this is going to be 22 if you want to follow along in your book. So firstly, we have W subspace of Rn and some vector V, where V is both in W and V is in W perp. This tells us that V is the zero vector. Is that true or false? So what's one of the characteristics of the zero vector? Well, we have this fact that the zero vector dotted with any other vector is going to be a zero for any vector u. And this is the only vector that does that. Every other vector, it's going to span some subspace, and when you dot with non-zero vectors in that subspace, it's not going to be zero. So let's see what happens if we take an arbitrary vector. If we take any vector u in Rn, then we can write u as u hat plus c, where u is in W, u hat is in W, and z is in W perp. So what happens when we take v dot u? Well, given this decomposition of u, we can write this as v dot u hat plus c, and then distribute to write this as v dot u hat plus v dot c, right? Now, because U is in W and V is in W perp, these two are orthogonal, and that term is going to be 0. And similarly, because Z is in W perp and V is in W, that term will be 0. So when we dot B with any vector, we're going to get 0, and that tells us it actually has to be the 0 vector. All right, so that is going to be true. All right, next part. So in the orthogonal decomposition theorem, each term in our formula, and I'll reference the formula again real quick so you can see it. Is itself an orthogonal projection of Y onto a subspace of W. So it's going to be asking about the terms in this formula up here, each of these individual terms. So like I said, what we're doing here is we're summing up all these projections onto individual lines, right? So if we have this basis for our subspace W, W equals span of U1 dot 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 UN, then each term of Y hat, oops, is the projection of Y onto this span of this singular vector here onto this line. That looks kind of messy, but yeah, so we're taking all these vectors in different subspaces of W, one-dimensional subspaces, and adding them all up to get our vector that's inside W, which is many dimensions. So this one is going to be true. All right, part C. If we have Y is equal to, Y is equal to Z1 plus Z2, where Z1 is in subspace W, and Z2 is in the orthogonal complement of that subspace, then we must have that Z1 is the orthogonal projection of Y onto W. We're essentially saying that Z1 is equal to Y hat. So this one's going to be true because of the uniqueness of this decomposition. When we write this vector Y as Y hat plus Z, these are the only two vectors in W and W perp respectively we can do this. If we take two other vectors in any other vector in W, there's no vector in W perp that we can add to get Y itself. So over here, if this Z1 is in W and this Z2 is in W perp, then we know this has to be a projection. If it was some other vector in W, then we wouldn't be able to find some Z2 because of the uniqueness of this decomposition. Okay, so then that guy is true. Now let's look at D. So the best approximation of Y by elements of subspace W is given by the vector y minus the projection of y onto W. And that's what we define Z as. So let's draw this out. We have this subspace W here, and then this vector that we want to approximate. So this vector inside W has to lie with a W, right? This Z here represents this vector in W perp, not actually lying in W. So this Z represents the actual distance. For the approximation itself, that's going to be the projection that lies within W. So we're actually looking for the projection of y onto W, not the original vector minus that, right? So that's going to be false. All right, let's do part E. So we have this matrix n by p matrix U with orthonormal columns. Then for all x in Rn, we have that U times U transpose x is equal to x itself. So what does this quantity UU transpose x represent? As I mentioned earlier, this is a nice way to actually compute this projection. So this is going to be a projection of x onto W, right? Where W is the span of the column vectors. Let's call them U1 through UN. Right. So what we have now is the projection of x onto W is equal to x itself. So when is this true? So if the projection of this is actually equal to itself, that's going to tell us that this vector actually lies within our subspace. Actually, this should be a P here. Let me see if I can find an eraser. I cannot do. There we go. Cool. So this only happens for x inside W itself, not x in all of Rn. And another way you can actually see that this vector has to lie inside W is, well, if you write x as this projection, right? Then because this is written uniquely, this other term has to be 0. So x has to be equal to its projection and lies within W, because this guy lies in W. Which is probably just saying this in too many words. So this isn't true for all vectors in R, and this is true for the vectors that actually are in the span of these column vectors. So that's going to be false. So let's move on to looking at a concrete, or relatively more concrete example of this interplay and decomposition. So this is going to be 23. And now we're going to look specifically at the null space and row space. So let A be an M by N matrix. Prove that for all x in Rn, x is going to be p plus u, where p is in row A and u is in null A. And then also show that if ax equals b is consistent, then there is a unique vector p inside the row space of A that solves the equation. So for the first part, we're going to use the, what fact we're going to use is the one from lecture before spring break, which now feels like forever ago. But these two spaces, null A and row A, are actually going to be the orthogonal complements of each other, right? So this fact that we can decompose these vectors is given by this theorem that these guys are orthogonal complements of each other. So we have, we can choose row A to be W, and that tells us that null A will be W perp. So if we try to decompose X into these two vectors, we can do it because of our decomposition theorem. And then we know that it's going to line up such that the first one is going to be in row A, and then the second will be in its complement, which is null A. So why does this actually give us this fact about this solution ax equals b for a specific b? So why does this tell us that firstly there has to be a solution in row A? Like why can't the solution just be like anywhere in Rn? Well, let's say we have some, since it's consistent, we know there's at least one solution in Rn. So let's call that solution x. Because for decomposition, we can write x as p plus u. Those are letters I used above, right? Yeah, p plus u. So if we have that ax is equal to b, then we have a of p plus u is also equal to b, which is ap plus au by linearity. Where does this vector u live in? U lives in the orthogonal complement of our row space, the kernel. So this is actually going to be 0. So that guy cancels out. And we have a solution with p in our row space of A. So next we want to show this is going to be a unique solution. So let's say we don't have a unique solution and there's two different p's that might work. So we have, right, p1, comma, p2, both in the row space of A, right? Now what we can do is we can firstly, what we're going to do is take the difference of these two guys, minus p2. And we have the constraint that these guys both are solutions. So I want to get some way of proving that these are going to be equal, if this is really unique. So the first thing I'm going to notice is that if I subtract these, well, if A on both these is going to be B, then A acting on this is going to be A acting on each one individually, which is 0, which tells me that this guy is in the kernel of A. And why is this useful? Well, remember that if we're trying to write vectors in our space, there's going to be only one way to write them as a vector in our subspace plus a vector not in our subspace. So the next thing I'm going to try to do is write this vector P2 is in our row space. So we can write it as P2 plus, well, 0. Or actually, I think in this case, I want to make these both P1. Yeah, so P1 is P1 plus nothing. But another way of writing this is we can write this as P2, which is in our row space, plus P1 minus P2. And these two are going to be equal to each other, but because this decomposition is unique, this actually tells us that P1 is equal to P2, and correspondingly, P1 minus P2 is 0 because they're equal. So since P1 is equal to P2, this solution has actually been unique this whole time. So we've shown that there's at least one solution. And then we've also shown that this solution has to be unique, which completes the proof. All right, I think that's all I wanted to cover from these two sections. But if you have any questions about this, something you want me to go over more in depth or something I glossed over, definitely just send me an email or let me know during next discussion. I can go back and recover it in more depth. Cool.